Hello everyone! I hope you are healthy and safe with your families. I would like to welcome you all to this webinar. My name is Priscila Lima. I am a Hydro School Coordinator at Voith, and I will be the moderator of this webinar today. Today we are going to talk about vibration phenomena in hydroelectric power units with my colleague Dr. Alexandre Neto. Alexandre has 15 years experience in hydro business and coordinates the special analysis team at Voith. Our webinars are important to connect us with our customers and to share relevant information on related topics. It's a pleasure to have you here, and I hope that you enjoy it. Now, let's get started.
Thank you, Priscila, for the introduction. Hello, everybody. Thank you for joining us today. We hope you enjoyed this presentation. So as Priscila mentioned, today we will talk about vibrations. That is a topic that is important in the daily activities of hydropower unit operators and manufacturers. So it impacts, it's a topic that is able to impact power units availability, operating conditions, and maintenance processes. It's also able to lead to catastrophic failures. From manufacturer sides, it influences several design criteria of components and verification during commissioning tests. So let me talk a little bit about myself. So my name is Alexandre. I am a mechanical engineer. I have master and doctor degrees in mechanical engineering at the University of São Paulo. I joined Voith in 2006, started working here at structural analysis in the product engineering department. Then I had the opportunity to work also at Voith in Germany. Back to São Paulo, I worked also in proposals engineering. And then I worked in the development and coordination of the special analysis and measurements teams in product engineering in São Paulo. So we are responsible here for special measurements, turbine efficiency measurements, vibration and data analysis, and special structural calculations. Welcome to our webinar. So our main purpose today is to put together the engineering mechanical vibration concepts and some practical experiences as well. Yeah. So during the next slides, I will guide you through a short introduction about hydroelectric power units. We will talk about mechanical vibrations, main definitions, and also a classification criterion. We will cover some vibration cases that will be free vibration, self-excited vibration, periodic forced vibration, non-periodic forced vibration, and then we will do a short closing. Yeah. So the goal here, is not to go deeply into mathematical discussions and concepts. So the idea is to present you each vibration case, followed by real examples from our market. So we hope you enjoy. Yeah. So in this slide, we have hydroelectric power plant layout. So we have in hydroelectric power plants, the conversion between hydraulic and electrical energies. So the water that is stored in the upper reservoir flows through a penstock reaching a hydraulic turbine. So at the power unit itself, the hydraulic energy is converted to mechanical and finally to electrical energy. Yeah? So this happens in the power unit inside the powerhouse. Yeah? In this figure, we have a very typical layout of a power unit driven by a Francis turbine. So it's quite, in this case, this is quite a huge power unit. The water that is flowing through the penstock, is reaching the turbine that is in the lower part of the figure. Yeah. So it enters the turbine in the spiral case, reaching the stavings and wicket gates, and finally the turbine runner. That is where the energy is converted into mechanical work. In the upper part, we have the generator, where the mechanical energy is converted to electrical energy to be supplied elsewhere. Then we have a short question for you. Yeah, please, Priscila.
Thank you, Alexandre. How many relevant excitation sources do you think can be found in hydropower units? You need to choose 1, 3, 4, or 5. So let's check the answer with Alexandre. Alexandre, tell us.
So thank you, Priscilla. Mainly, we are talking about three main excitation sources acting in hydropower units. We have mechanical sources, such as, for example, unbalance, electromagnetic sources, such as the ones that are induced by electromagnetic forces acting on the generator, and hydraulic forces, which comes from the fluid dynamics. Each excitation source has its own complexity. And the complex combination of forces of different natures that acts in different moments or different operating conditions, they determine the dynamic behavior of a complete power unit. So let's talk now about mechanical vibrations. Mechanical vibrations are periodic motions, so that means it repeats itself after an interval of time. In a simple oscillatory system, we have a periodic exchange between elastic or gravitational potential energy and kinetic energy. So this is the mechanical oscillation. In hydraulic oscillations, we have the periodic exchange between kinetic and pressure energies. So the most fundamental mechanical vibrator that will be a useful concept that we will use in the next slides is a mass hanging from a spring. When there is no motion, the force of gravity pulling the mass down is balanced by the force of the spring pulling it up. And then the mass is at rest. If the mass moves away from its equilibrium position, it has one given displacement. If we don't have any kind of energy dissipation in this ideal system, that means if we don't have any damping, the system will oscillate indefinitely by the effect of acting forces around the equilibrium position. In this figure, we have here on the right side, we have one graph that is a graphical representation of the displacement or of the mass position. The main parameters we can identify in this graph is the initial position of the mass, the maximum displace around the equilibrium position, that is the amplitude of the movement, and the period of time in which the movement repeats itself, that is the period, and the inverse of the period is the movement frequency. So now talking about the types of vibrations, so force of different natures can induce different responses in hydropower units. The types of vibration we will cover here, so can be classified in autonomous vibrations and externally excited vibration. So this classification criteria classifies it according to dependency of external sources. Autonomous vibrations can be divided in free and self-excited vibrations, and externally excited vibrations can be divided into forced vibrations that can be periodic or non-periodic or parametric vibrations. So let's talk a little bit about free vibrations. So what are free vibrations? So free vibrations are the system dynamic response after one single initial energy introduction. When you get, for example, the mass and apply one single energy input, so it will oscillate. So if we go back to the mass spring oscillator and consider one additional element, which can be seen here as the damper, which is some additional, which represents actually the energy dissipation. So one can see that the mass, after this initial energy introduction, the mass will oscillate and go back into the rest or equilibrium position. And this is quite a useful behavior to us, since the system is vibrating at natural frequencies, and this phenomenon is applied for natural modes and frequencies identifications. Yeah. So the graph on the right side shows what would happen for a linear damped and stable system. So the body would oscillate and go back into the equilibrium position. Yeah. So example of free vibrations in daily applications, for example, when somebody thinks about one guitar, yeah, the strings of the one guitar are played by plucking. Yeah, so the string is pulled away from the equilibrium position with some initial displacement pattern and then released. So then it vibrates in natural frequencies and produce the sound we can hear, for example. Yeah. For our hydropower business, we have experimental model analysis or bump tests as some kind of applications. Yeah. So what is an experimental model analysis? Yeah. So in this technique, yeah, the finite points of the structure are excited by known impacts. So the structure to be identified is completely mapped. Yeah. Points of the structure are excited by impacts of one instrumented hammer. So we measure and record the force being applied to each of the points. The response of the body is measured and processed together, and the main outcomes are frequency response functions of structures, mode, shapes, and eigen frequencies. So this is quite useful for us because we can, by using this technique, we can evaluate, we can have natural frequencies, natural mode shapes, yeah? And we can use the results to calibrate numerical models or to help us understanding the real observed behavior of a given component at site. Yeah? In the pictures from the slide, we have the typical instrumentation used for such tests, such as the impact hammer and accelerometers. During the tests, the accelerometers are put in a given component to measure the system response. Yeah. And then after the post-processing, one can see, as we can see here in the right side, the natural mode shapes and even compare with calculated results. Yeah. So this is quite a useful behavior for us. Now let's talk about self-excited vibrations. Yeah. So this is quite a complex phenomenon. Yeah, so this phenomenon depends on an external energy supply, and the alternate force that sustains the motion is created or controlled by the motion itself. So if the motion stops, the alternating force ceases. Yeah. So in the previous phenomenon, in the free vibrations, we have introduced the concept of damping, which is a force that normally is proportional to the movement velocity and opposite to it, that is representing the mechanical dissipations. One point of view or one possible modeling for self-excited vibrations is to see the system as if it has negative damping. The damping acts proportional to the motion velocity and opposite to it, as I have mentioned. Negative damping is also proportional to the body velocity, but has the same direction. So therefore, one can see here in this slide, in the upper right part of the, in this graphic, in the upper right part of the slide, that the amplitudes, considering this assumption, would increase indefinitely. Yeah. In most real systems, the mechanisms of self-excitation and energy dissipation, they coexist and they are separated. So therefore, the system has a very nonlinear behavior, and the real damping limits the system oscillation amplitude. So this is what we can see in this lower part graph. Always the response of the system is a natural frequency. So, and when this occurs in the hydro business, so when we are talking about gap flows, overload operation in Francis turbines, flow along slender structures, intakes, gates during emergency closings, and water gap of Kaplan turbines. One example here is of self-excited vibrations and related to gap flows are self-excited vibrations in a Francis turbines. Yeah. This was a power plant refurbishment, so already existing Francis turbines at site were put back into operation after a modernization. Such machines have already faced such problems in the original machines commissioning with the original manufacturers. And after 4 power units were put into operation, so vibrations appeared for a maximum power condition during the commissioning. Yeah. So in the beginning, we were able to see very high shaft oscillations, as one can see here in this graph from the left side. Yeah, so suddenly in high power condition, the vibration increased significantly. After we have evaluated the signals, we could see that additional frequency components became evident on the signals. Yeah. And those additional components were associated to the shaft line eigenfrequencies. So this gives us a very good indication that this could be related to some kind of self-excitation phenomenon. Yeah. And then by evaluating the historical background and design conditions and by doing further analysis, so we came to the conclusion that this was caused by a self-excitation mechanisms caused by the runner seal arrangement and side chambers geometry. That this is the region that is indicated in this upper right figure here. Yeah. So we did a slight modification of the side chamber. We changed the flow condition in the labyrinth, and then the self-excitation source was eliminated after all without the need of disassembling this power unit. Yeah, so the problem was completely solved. Yeah. So you can imagine here, yeah, we have a medium, almost a medium sized Francis turbine that was running into resonant condition during the commissioning phase. So we have a rotating machine with hundreds of tons of weight running into resonant conditions. So you can imagine the amount of energy which is involved in such kind of phenomenon. So it's a quite impressive phenomenon here. Yeah. Another kind of vibration is the overload operation in Francis turbines. Yeah. So Francis turbines operating in off-design condition, they have swirling flow components in the draft tube, yeah, that leads to the presence of draft tube vortices. Yeah. Talking specifically about the overload vortex, it typically has one axisymmetric shape. So it forms one axisymmetric vapor cavity, yeah, that can lead to a hydraulic system overall instability. Yeah. So this, as I mentioned, this happens in off-design conditions. This is already away from the design operating condition for a given Francis machine. This example that I bring to you, this happened here in Brazil. So the customer wanted to test the machine operating in overload condition. And during the test, we could see pressure pulsation increase. Yeah, so already above 20% of our reference flow, the pressure pulsation and the power oscillation levels started to increase. Yeah, reaching almost 14% of the reference head. Yeah. If we take a look in the signal, so in normal operation, we have a pressure signal with, let's say, stochastic characteristics with a not so defined frequency components. Yeah. Then when the amplitude started to increase, we started to observe a more sinusoidal component, yeah, with a very clear frequency, in this case around 50% of the rotating speed of the machine. And then finally, with the complete phenomenon developed, we could see a very nonlinear system characteristics, or we can see in the several components, several frequency components or higher harmonics present in the signal with a nonlinear behavior. Yeah. So outside the continuous operating range of a machine, a possible solution for that could be changing the system's dynamic parameters by, for example, doing air injection. Yeah. So not always, for instance, machines are operating into overload condition. Yeah. So this was a supervised test. Yeah. And this is a more rarely observed phenomenon. So, but this is one kind of example of self-excited vibrations. Now we can go to forced vibrations and talk about periodic vibrations. Yeah. So this is the most applicable case in our daily work. Yeah. So going back to our oscillator model, yeah, one can see here that we have added one additional element, yeah, which is the excitation force. Here, the system excitation is given by a periodic force, yeah, and the system is vibrating at the exciting frequency. Yeah. So this is the case in which we have a given force exciting the body, and we see that the force is responsible by the body movement. Yeah. Initial conditions can change the response of the body for undamped systems, and in real damped systems, the system response is independent of initial conditions. Yeah. And always when we talk about periodic force vibrations, the topic that comes to attention is the so-called resonance. Yeah. So the word resonance is often used and misused in common vibration discussions. So what is resonance effectively? The resonance phenomenon occurs when the excitation frequency is close to a natural frequency of the system. Excitation frequency is close to the natural frequency, the system amplitude can be significantly amplified, and the resulting vibrations are really huge. So it's very common to see this graph that we can see here in the right upper part of the slide, yeah, in which we have the relative displacement in the vertical axis and the frequency ratio in the horizontal axis. Frequency ratio is the ratio between the excitation force and the natural system, the system natural frequency. Yeah. So when it gets close to 1, that means when the excitation frequency reaches or matches the system natural frequency, we have a very high dynamic, we can have very high dynamic amplification. Yeah. And the damping acts also as has a crucial role in this graphic representation. One can see that a higher damping reduces the amplification occurrence here. Yeah. So resonance conditions are completely avoided during the design phase of new components. Yeah. So this is something really important to us. Yeah. And examples of periodic force vibrations, not necessarily resonant. So we can have unbalanced, mechanical, electrical, hydraulic, rotor stator interactions, the part load operation, vortex operation, the part load operation vortex in Francis turbines, and von Karman vortices as well. So talking about mechanical balancing, yeah, so non-uniform mass distributions on the rotor leads to unbalanced force. Yeah. Mainly the rotating frequency is the major impact. Yeah. And one can see here one typical example in which we had shaft oscillations here on the left side for a given machine. And after a balancing mass was added to the system for balancing correction, one can see that in this case we had almost a 50% reduction on the shaft oscillation vibrations. Yeah, in this example. Yeah. So this is taking into account for components design and a special balancing process during commissioning phase is done in order to assure that unbalanced levels remain within the acceptable ones. Yeah. So this is example. This is again, we are talking here for our hydro machinery applications of a non-resonant condition. So this is simply a periodic force vibration. Yeah. When we have, for example, also magnetic eccentricities, for example, or non-uniformities in the magnetic flux, this can generate unbalanced radial forces. So those forces affect vibration, and they depend on the intensity of the magnetic flux. Yeah. So here on the right side, one can see time signals of shaft oscillations as well. So they are measured in the bearings. And after the excitation system of a given machine was activated, so then the oscillations were just increased by the effect of magnetic imbalance. The solution for such kind of I wouldn't say a problem, or for this kind of characteristic would be just to try to identify and correct the sources of unbalanced magnetic loads. So for example, checking for assembly conditions or short circuits, or yeah. And another possibility would be to try to do some magnetic balancing. Yeah. So here you can see the detailed signals for non-excited condition and for excited condition. Another very interesting phenomenon, related to periodic force vibrations is the so-called rotor-stator interactions. Yeah, so they occur especially in high-head turbines or pump turbines due to the proximity between runner blades and wicket gates. Yeah, so in this kind of occurrence, the stationary parts, they feel the excitation forces associated with the runner blade's passing frequency. And the rotating parts, so for example, the turbine runner, yeah, they feel the excitation forces associated with the wicket gate's passing frequency. Yeah, so this is quite, let's say, a complex interaction phenomena that leads to periodic forced vibration. Yeah. Also, for this case, mitigation measures are taken into account during the machinery design phase to reduce the force's amplitudes, yeah, and to avoid resonance conditions related to this occurrence. Talking again about Francis turbines operating in off-design conditions. Yeah, when talking about Francis turbines operating in part load, so it has higher swirling components in the draft tube flow that leads to vortex rope breakdown, yeah, and vortex rope. In part load condition, we have a rotating vortex rope present in the draft tube that leads to unsymmetrical periodic distribution on the runner blade. Yeah. So this happens most part of the times from 50 to 80% of the optimum flow. And it's more relevant for higher specific speed turbines. Normally, the frequency associated to this vortex movement is below the machine rotating frequency, and it stays between 20 to 40% of the rotating frequency. Yeah. So one can see here in this graph the relative shaft vibrations of a Francis power unit. And we have the generator guide bearing vibrations and the turbine guide bearing vibrations, each one measured in 2 different planes. And one can see that here in part load conditions, we have a sudden increase into the shaft oscillations for part load conditions. And this is associated with the part load vortices. Yeah. So this is what is being shown here in this part of the graph. Okay, another kind of very interesting phenomenon is the so-called von Karman vortex shedding. Yeah, so this happens because of the flow around immersed body under particular conditions. One can have one periodic vortex wake of vortices that are being shed from the trailing edges that induces pressure oscillations along the body that leads to vibrations and also to resonance. Yeah. So the coincidence between the vortex shedding frequency and the body natural frequency leads to a resonance. One kind of this occurrence, so this kind of occurrence is related to Staving vibrations. So Staving vibrations are problems that were firstly reported around the 70s. Yeah. And until today, there are power units that have operating conditions impacted by this phenomenon. And despite the fact that the solution is quite well known and avoided in new machines. Yeah. So in these figures, we have a project that was developed by us together with one customer to investigate Staving vibrations that were leading to cracks and power units output restrictions in a very large hydropower plant located in Brazil. In this case, we did several investigations. We were able to do Staving fluid structure interaction simulations. So here in this figure on the left side, you can see a short animation of the vortices being shed from the Staving trailing edge. We were also able to do special laboratory investigations. Yeah, so you can see the trailing edge profile here and the vertical structures in the flow here in this green color. Yeah, and also we were able to do prototype measurements and check this actual Staving behavior. You can see that when this graph shows stress oscillations measured by strain gauges, and in high load conditions, the stress amplitudes were significantly increased. So this leads to fatigue damage and fatigue cracks, which should be repaired. Those components are associated to the Staving natural frequencies. Yeah. So that means we are ahead of resonant conditions. And yeah, in the end of this study, we have proposed Staving profile modification that was able to eliminate the occurrence, yeah, and solve the problem. Now let's talk about non-periodic force vibrations. So in this case, the vibration of the dynamic system is excited by forces with transient or stochastic nature. So they are forces that are not constant along the time as we had for force vibrations. Yeah. So in this case, no initial disturbance is necessary. Yeah. And some examples in which this phenomenon occurs are related especially to transient conditions. So for example, startup, very low part load operation for Francis machines, or cavitation related phenomenon, load rejections, or load change procedures. Covering here the startup conditions. So during startups, stochastic vibrations are present due to flow misalignments. So the machine is stopped. We have very small wet gate openings, very strong flow separations, yeah, and flow misalignments, turbulence, and other transient phenomena are present. Yeah. So as a result of that, a broadband excitation can be present during this condition. Several natural modes can be excited, yeah, and leads to vibration until the machine reaches, let's say, its proper operating condition. Yeah. There are investigations that can be done to optimize the startup sequence and the acceleration of the machine, yeah, to reduce the startup damage and increase the machine lifetime. As one example, one can see here in the graph some measurements done in a turbine runner blade, in a Francis runner blade during the startup condition. One can see in the lower part of the figure in the blue color the rotating speed. So this means until it reaches 100% of the speed, and the white gate openings. So this is the white gates openings. It indicates that the white wicket gates were closed. It started to open, letting the water flow through the turbine, until it reaches the rated speed condition. And one can see here in the upper part, the stress is measured directly on the runner blade. So you can see that it's not constant. It has several different amplitudes along the time. Looking at the frequency components present on the signal, one can see several frequency components as well. So it's quite a transient and variable phenomenon. So this is some one kind of example. So talking about a little bit about very low part load operation for Francis turbines. So stochastic vibrations are also present in low power condition output for Francis turbines. In this condition, so the flow is quite misaligned. We have the so-called channel vortices, which you can see here, for example, in the simulation images here in the upper part of the figure. And here in the reduced model test, one can see also the channel vortices here in between blades. And one can see that these flow separations and these channel vortices, they induce stochastic vibration components, and higher vibration are present in overall the power unit with broadband excitation. So here, taking a look into the shaft vibration signals in the left part of the figure, one can see higher vibration levels when compared to the rated operating condition, or to the optimal operating condition. So this is related to the very low part load behavior of a Francis turbine. And now we have time for another question for you, which is related to cavitation. So please, Priscilla.
The question is, what is the expected frequency range for the cavitation phenomenon? Less than 10 Hz, 10 Hz to 100 kHz, or higher than 100 kHz. Let's choose. So let's check the answer with Alexandre.
Thank you, Priscilla. So cavitation leads to acoustic emissions of very high frequency. So normally we are talking about megahertz. So the third alternative is the correct one. So what is cavitation? Cavitation is the phenomenon that occurs when the pressure drops below, the water pressure drops below the vapor pressure, leading to the bubbles, the vapor bubbles formations in the flow. And when the pressure increases again, the vapor bubbles are collapsing, and micro water jets are hitting the surrounding surface, damaging it. So this leads to cavitation erosion. So the phenomenon occurs at very high frequencies. And this is not often detectable by means of conventional measuring chains. The conventional measuring chains that are used into the daily hydropower applications are normally able to detect lower frequencies, so associated to the machine rotating frequency, or pressure pulsations, pressure oscillations, but they are not going into very high acoustic emissions such as megahertz. So in this figure, you can see one schematic representation of the bubble behavior, as I have mentioned. And one can see here in the upper part of the slide, the formation of cavitating bubbles in a model test. Yeah. And in the lower part, this lower picture, one can see the erosion damage caused by cavitation. Yeah. So now it's time for our closing remarks. Yeah. So it's important to know that the power unit behavior is a result of the combination of complex multiphysics phenomenon. So from the topics we have covered, we have divided and classified each of the vibration phenomenon in according to the dependency of external sources, but in reality, they are able to occur in a simultaneous way. Yeah, so unbalancing happens together with hydraulic excitation sources, or with electromagnetic sources, and then we have to be to take care and be systematic to be able to separate each one of the excitation sources to be able to solve an eventual machine problem. Yeah. And the proper identification and evaluation of this phenomenon requires understanding of the associated physics and modeling, the adequate design of tests, monitoring system, and related measuring chains, and also analysis tools, yeah? And also experience with the associated mechanical, electrical, and hydraulic design. Yeah? With more than 150 years of experience in the hydro market, Voith Hydro is capable of performing proper monitoring, data analysis for a complete diagnosis of a power unit. Yeah. So this specific knowledge also allows us to develop products and tools that are able to capture hydropower associated phenomenon. We are also available here, yeah, as you could see. So all those cases that we have shown here, they are related to real occurrences, and we are able here to provide you expert knowledge and to work together with you for doing vibration and other process related data analysis. Yeah, we can offer you expert engineering services. So we are able to assist you with dedicated measurements and for doing assessments for power unit components. We have on performance lab for doing expert data analysis. We can do remote engineering support. So we hope you have enjoyed our webinar today. We hope we have enjoyed the topics we have covered here. We stay available for you. This is our contact data. We stay available for contact for questions, and thanks a lot for your time here with us.
Regarding generator balancing, low vibrations level mean that the machine is balanced?
Okay, good question. In this case, so balancing is done to ensure proper mass distribution and proper principal shaft alignment. So in this case, low vibration levels not necessarily means that the machine is balanced according to the desired balancing grade. So therefore, special balancing procedure is takes place during the commissioning phase in order to ensure that the balancing grades have been achieved.
Great. Another question here is, which techniques are being used currently to measure cavitation indirectly?
Okay, so as we have mentioned, cavitations, they occur in a very high frequency range. So therefore, we need to have special measuring chains to detect cavitation from in an indirect way in prototype measurements. So therefore, we have sensors of acoustic emissions able to read very high frequencies of emissions, and And we have also developed together with one university in Germany a cavitation monitoring system that is able to read and detect cavitation and show the cavitation intensity during its occurrence.
Okay. The next one is, which measures can be taken to reduce the effects of partial load vortices?
Okay, so I have seen that this topic also appeared more than once. So I think this is a good topic and a topic of major interest. So there are mitigation measures that can be taken if the intensity of pressure pulsations are high for part load vortices. So of course, each case should be evaluated or studied individually in order to check which is the phenomenon that is happening. So by means of measurements and dedicated measurements. But for example, air injection is able to reduce pressure pulsations intensities, or draft tube fins installations or special geometrical arrangements can be also applied to reduce the vortex intensity.
Good. The next one is, why do you use an accelerometer in a journal bearing? What kind of fails do you expect to find with that sensor?
Yeah, okay, so also this is a very good question. So to use accelerometers in the bearings, it's quite a useful practice, and they are used in temporary measurements and in monitoring system measurements as well. Accelerometers are used to measure absolute vibrations in the bearings. So they are used to provide us one kind of indication of the forces that are being transmitted from the rotating part to the stationary parts. Yeah, so we use the vibration levels measured with accelerometers to evaluate, let's say, if the machine is running into a smooth condition, and compare vibration levels with the levels that are foreseen in standards, for example. Yeah, so this is why we use accelerometers in the bearings.
Okay. How did you come to the conclusion? Where do you need to modify the chamber?
Okay. I would say that I am understanding that this question is associated with the Francis turbine self-excited vibrations. So in this case, so as I mentioned, we did the frequency component analysis to check which were the main components present on the signal, and we could identify that the vibrations were occurring at the shaft line rotating frequency. Therefore, we did simulations to check the shaft line parameters, and also checked the coefficients that we got from that particular side chamber and labyrinth arrangements. With those coefficients, we designed these small modifications that were added to change the flow conditions through the labyrinth, and then the problem was solved by implementing these modifications. So those were the further engineering steps that we did in order to solve the issue. Yeah, so it's not only a matter of measuring, but also doing analysis to find the best solution. Yeah.
Okay. The next one is, how it was vibration concluded it is due the side chamber.
Okay, I think this is the same, yeah.
Okay. What is wheel standard vibration and threshold for Francis?
Okay, yeah, good question as well. Vibration limits for every kind of hydraulic machinery are obtained or are used, are obtained from standards. Yeah, so we have ISO standards that have vibration limits that were obtained in a statistical way, and the kind of, or the limits are a function of the arrangement of the machine, the bearing arrangements, the bearing radial support against the powerhouse concrete, and the overall machine arrangements. And the vibration levels are classified according to this standard in 4 different ranges, and those are the limits that are considered in our market. So they are the limits that comes from the standard.
Great. The next one is how can pulsation can be reduced or avoid in a Francis machine?
Yeah, so this is also regarding the one of the first questions. So this is quite a recurrent topic. Yeah, so as I mentioned, there are actions that can be applied to try to reduce pressure pulsation levels, and in each case, there will be one best solution that can be applied. So air injection, geometrical modifications, draft tube fins, and so those are some kinds of examples. Yeah.
Okay. And the next one is in Portuguese.
For self-excited, vibration could be considered periodical. Yes, the self-excited vibration, they are periodical. And in our classification, the classification proposed there is according to the periodicity of the external source that generates the vibration. The phenomenon is periodical. It repeats itself in undetermined cycles. In Portuguese, so with this regard, for high load vortex, the turbine wasn't with air pressure. Yes, in these signals that I've just shown you, they were effectively a control test, okay?
Ok. Ahora en español. ¿Cómo se conoce la frecuencia natural de la máquina?
Ok, bueno, voy a intentar responder en español. Me perdón si no...
I'm sorry if it's not correct. The natural frequency, all the components, they have their natural frequencies individually, and the rotation part, they also have a natural part in the whole group. In the design phase, the natural frequencies of the main components, they are checked in an analytical or numerical way. That is, they are checked beforehand, and if you want to get to know the natural frequency of a component at site, so we can use the example of the free vibrations and bump tests. With instruments, you can excite a structure in predetermined points, and then you can do a processing of the data processing to have the vibration modules and the natural frequencies associated with it. So today in Brazil, we increasingly need power units that are broad, and we coexist with vibrations and minimal power generated by a hydraulic chain. Do you have any example of self-excited conditions of turbines in this condition? It was partially answered. I don't know if you want to mention anything else. Well, broadly speaking, the graph that I showed you in the part load, you had the increase of the vibration on power or flow power, and then we had the part load vortex that were present. That's the typical behavior. looking at the domain of the frequencies and vibrations. If we could see the characteristic frequency of the part load vortex, we can later on, if you want to get to know other examples, get in touch with us, and we can try to discuss it and show you more examples, without a doubt.
Legal. And in English now, Dr. Alexandre, nowadays, what is done to avoid this type of phenomena, von Karman?
Okay. So let's say a first order factor that influences von Karman vortex shedding is regarding the geometry, and modern turbines or modern design turbines, they have geometry profiles that mitigate the occurrence of von Karman vortex shedding. But nevertheless, if they occur, the best thing to do is also to try to modify the geometry in order to reduce at most the von Karman vortex street intensity and change the vortex shedding frequency. So that means that they are not coupled to the body natural frequency and not leading to resonance. So this is, let's say, the basic approach. Yeah, but for new machines, the geometry profiles already ensure proper mitigation of its occurrence. Yeah.
Okay. Can you specify the type of strain gauge to use to determine vibration Francis turbine stavings?
Okay. When we need to do direct stress measurements in underwater components, stavings or even runner blades, we use special strain gauges that are waterproof, and also we take care with the wiring and also with special coating in order not to have them washed out through the by the flow. So this is the kind of strain gauge that we use for such kind of complex and severe applications.
Great. The next is in Portuguese. Essa emissão acústica.
So this acoustic is only because of the implosion of the bubbles, or it's the impact of the microjet on the metal? That's a good question. Both phenomenons. To generate acoustic measurements, so the bubble formation, the position of the microjet can generate this acoustic shedding. Most of the times they are low intensity, high frequencies. They are challenging situations to detect. So the frequency range should have a vibration sensor for the management of this issue. An accelerometer to measure this oscillation must be able to measure frequencies in the typical range of the operation of the rotation frequencies of a hydropower generator. They are at lower frequencies, so it's important to look at the maximum frequency, the capability it has, and I'm talking about it in a broad way. So the accelerometers, they have reading capability of up to 10 kilohertz, and given to the rotation frequencies that we have, it's important to observe the frequencies which are lower the accelerometer to be able to read frequencies below 10 hertz. Alexandre, do you have any example of vibration case with a vibrapattern, vertical or horizontal? Yes, we do. At the moment, we've been commissioning Pelton turbines. We have some examples of these kind of turbines that we could discuss them. If you have any specific detail, you can get in touch with us and we will support you for sure.
I don't know if you have more time, Alexandre. We have a lot of questions here.
Yeah, maybe we can select 2 or 3 more, and then we can try to address the others directly
via
by
email.
email. Yeah.
I don't know if you need to choose something.
No, please.
Okay. Question to page 15. What can be done to reduce the risk of such vibration in the area of the runner side chamber?
Okay, so I think that, so this normally the geometrical characteristics of labyrinths and labyrinth flows and also current geometry already takes into account, let's say, normal characteristics that are not associated to this kind of occurrence. Yeah, nevertheless, during commissioning tests, so this is also checked that no unexpected vibrations are taking, or they are occurring in normal machine operation.
Okay. Una em espanhol ahora.
So the electromagnetic displacement upwards, downwards in the assembly process influence on the vibration levels. In theory, they might influence a magnetic load, shaft 1, but it shouldn't influence the radial vibrations, but it depends on the electrical characteristics, the magnitude of the forces that will align the center of the runner of the generator. Voith supplying online monitoring device based on database or only periodic services by a Voith expert. We have our monitoring system, online one. It's on Care Health Hydro, and all these characteristics of the phenomenons which are associated with it, with vibrations, dynamic behavior expected from power units, they were taken into account in the development of the system. So there is this hardware. It allows you to measure several parameters simultaneously, not only vibrations, but also parameters that come from supervisory systems or parameters such as pressure, and allows the correlation of data, and so that you can have a diagnosis. So the answer is there is this dedicated hardware for it. And our performance lab also works with data generated by the systems in order to do automated diagnosis and apply data analysis techniques to the signal processings which are generated by power unit.
Okay, I think that's it. If you say thank you for the people.
Yeah, so thank you everybody again for joining. It was a pleasure, to share our experience with you. We will go through your questions and hopefully we'll be able to answer directly to you within a few days. And thank you very much again. And we are available if you need assistance. Please just contact us.
Yes, thank you everybody for your time. And it's important to remark that Voith has several online courses at Hydro School, and you can check the availability on our website, and our contact is there too. Thank you so much and see you.